Okay, well, welcome everybody. I hope you're doing well and that we're getting ready for a little bit of a respite, hopefully, on the weekend. Today we have session 13. We're going to talk more about beams, or more going to be lots of discussion about beams. Before we get going, though, are there questions administratively? I know there were kind of a few announcements on things. Okay. Well, I would like to introduce Trevor. Okay. He's our TA. I know some of you have interacted with him in office hours. And what we're doing is having an opportunity for him to join us so that there are a couple of us here that can answer questions. And this is the time where everyone's available, right? Technically, so it's more accessible. You can get to the TA this way, okay? Um, and then, so kind of for today, we're going to essentially let people work independently, let people work together, attempt to answer questions on session 12 questions, which we postponed their due date until Tuesday. And now we have a new session, session 13. And those are also going to be due on Tuesday. But I think my guess is that we'll find those except for the third one, significantly less demanding than the last assignment. So I'm not too worried about the overlap, okay? For this session, by the end of it, okay, we should have the following skills or knowledge, okay? Pretty much just two things. Relate the radius of curvature to longitudinal strain. Okay, and there will be some compressive or tensile strains involved. And the other one is essentially relate bending moments we're talking about beams, of course, so we're talking about transversely loaded beams. Relate bending moments to bending stresses. Okay, and these can be compressive or tensile. And kind of en route to get to this understanding, we're going to have to do a little bit of math. So you're going to see some descriptions, quite a bit of description actually, on second moment of area. And it's a little bit confusing at first, but once we get the hang of it and we understand the parallel axis theorem, it kind of becomes a little bit of fun. All right. So people are often wondering, okay, what are the equations that I need to keep in mind? Well, this equation for relating the strain to the radius of curvature is given by epsilon equals minus y over rho. Y, as you'll see in the videos and in the problems, is the distance from the neutral axis. Okay, and the neutral axis is the axis that doesn't have any compression or tension on it. It curves, but it doesn't change its length. The other big equation, the huge equation, okay, that everyone will now go the rest of their life remembering, okay, is that sigma equals negative my over I. So sigma being a longitudinal stress or a bending stress or a normal stress along the beam, and m being the internal bending moment, y again being the distance from the neutral axis, and I is the second moment of area. Okay, so those are kind of the two big equations. A lesser one, okay, but nonetheless important, will be second moment of area. Second moment, well, that's what it is. Second moment of area for a rectangular cross section. Okay, and so this is kind of famous as well. I equals bh cubed over 12. Okay, so that's one that you want to kind of put in your memory banks and you put on your sheet. But as you walk around the world, you'll be like, oh, there are beams everywhere. And I is how much they resist bending moment to create either a stress or a strain. And I is bigger when the thickness is bigger, at least big time, because h is the thickness, and that goes with the cube. Width, it's a linear increase. Okay. So that's another equation, and then I guess the parallel axis theorem is another one. So you have the individual components of the second moment of areas, and you can think about them in terms of their area, okay, and the distance of that area, the centroid of that distance, to the neutral axis, okay, or essentially the axis of rotation. If you're thinking about moments of inertia, right, thinking about polar moments of inertia, or the parallel axis theorem that you may have seen before. Often it's described with, instead of an area, it's often described with a mass, okay, but here we're describing it in terms of area, because these are second moments of area. Okay, and if the density is constant, then area and mass would be proportional to each other. Yes? What's the B? Oh, over here? For this one? Yeah, this is the width. B is the base or the width of the beam. Okay, H is the thickness of the beam. And one thing to keep in mind is that I is going to have units of length to the fourth. Okay, so you're going to see a lot of meters to the fourth when you do these problems. Okay, that's pretty much what I have. Other announcement: the exams have been graded. Really heroic effort by Trevor to do this quickly and efficiently. Okay, and so at the end of the class, we don't want at the end of the class we'll pass them out. And yes, it is in person that we distribute the exams, and it's not just in person, it's like person to person. Years ago, I had someone who didn't appreciate having the exams just laid out for everybody in the class to see. So it's not that big a deal, so we hand them out individually. All right. Okay, so let's get to it. I'm happy to go back and talk about session 12 stuff with people, and I'm happy to talk about session 13 stuff. I'm happy to talk about Pre-Pro Max. If you have questions about Pre-Pro Max, you might want to actually talk to Trevor. He can help you there. He can help you with anything, but that's one of the things. Oh, and I guess just in terms of resources, what I've started to do on this OneNote, which you can all access, all right, I have a tab here for office hours, and so I have been doing office hours on the board, but I've started to do them on OneNote, and so if you miss an office hour and you're kind of interested in what we talked about, I'm going to try to do it here, and it's going to be a little awkward, but for the people who come to office hours in person, I'm going to have them essentially log into Zoom, and we'll talk to each other in person. Okay, great. All right, let's have some fun. in. Okay, we'll be curious. Please feel free to collaborate. Okay, that sounds great. I would suggest that that first video that I posted for session 13 is really long. And it's not much in the way of equations that come out of it. Okay? I would listen to that one on 2x. Okay, to get through it. Okay, well, I mean, we can talk about that a little bit with the pre-pro max.
I just think there might be something I'm missing. Like, yeah, I made the material and the.
This is it's even doing it to me. It needs to be extracted. So here, hold on a second. See, this is my own mess. This has been a problem for some people. Okay, so here I have it extracted. So when you're looking at this, is the strain not coming out correct, or what's not coming out correct?
Yeah, the strain wasn't coming out right. It was like way off. It
Okay.
was the same order of magnitude at least, but
Okay.
that was about it.
So one thing, when you imported it, all right. So first we do new, right? We bring it in. You have these units because one thing that can happen. Did you scale it down by 1,000?
I might have had millimeters, tons.
Okay. So
seconds.
well, that could be one part. So that could be one part. The other thing that can happen.
But it was the right size, like based off of this thing.
It was okay.
Yeah.
Well, that's a good sign. All right. So now if I go, I don't even know where I left mine. I might have to go to FreeCAD to do it again. Okay, but let me see if I can find mine. So, sure, this is a cylinder. This will probably come in. Let's see what it looks like. I'm not 100% sure. Okay. So when I see this one is definitely like it's definitely too big, right? You can see that it's at 88 meters.
It's supposed to be 8 millimeters.
It's supposed to be 100. It's supposed to be 100 millimeters, right? So one of the first things that you want to do is come into here and go to Part and do Transform and Scale. And then you want to make sure you scale. And if you did it in SolidWorks or you do it in FreeCAD, I'm not quite sure. Both of them gave me issues with the scaling. Okay, and that's a common problem with STL files. So you have to check, right? You just have to check. So here I just do.
Could it have been scaled by like, because it looked, it looked like it was the right size. Like it was about 90 millimeters long. Could have been off by a little bit because of SolidWorks. And
Probably not.
be like a
As
whole
long as
10?
I mean, as long as you got it down like right. So this is now really small, right? So it's zoom to fit, right? So now, now it's 0.008 here,
Yeah.
or 0.088, right? Millimeter or meters, right? So we know that that's correct. And I'm gonna bring this over here. So I have mine on the x-axis, all right? One of the things that can happen as well is that we can get a little bit, we all can get a little bit kind of twisted around when we're looking at the shear stresses and the shear strains. So we recall that, they are coming off parallel to this face, right? So if I say this is 1, 2, and 3, right, for x, y, and z, which stresses, if I'm looking for shear stress or shear strain, which ones am I looking for? Am I looking for 1, 1, 2, 2, 3, 3, 1, 2, 1, 3, or 2, 3?
1, 2.
So 1, 2, yes, is a good choice, right? So that would be on the x face, right? And it's in the y direction. And where is 1, 2 going to be a max? Yes.
The opposite side of the fixed end.
So it's
Of the
going to be
twisted end?
at the max z and the max z and the minimum z. So if I'm looking at 1, 2, right? I'm looking in the 2 direction, which is up here, and we have the maximum stress, right? It goes radially, so it's going to be, I'm going to be looking like down here if I was twisting this direction, okay, or up here, and the same thing over here. Okay, but up at the tops, at plus or minus maximum y, if I'm looking at 1, 2, I'm going to see very little. Okay, because the shear stress is running in the z direction.
So could I have been looking at the wrong node?
We could have been looking at the wrong node, could have been looking at the wrong direction. That's kind of what I'm getting at, right? So like,
Probably what it was, because I checked my settings like 50 times.
okay, so like, cause I think last time, yeah, here is where I discussed it, and this is all online, right? And that, look, if we're looking for, you said tau 1, 2, right? You see, this is the z direction, so we're up at the top. We're at the bottom where we're going to have our maximum tau 1, 2, right? 2 is the y direction, right? So this is the y direction. This is the z direction, right? But tau 1, 2 is going to be at a max z or minus z in terms of position. Okay, because the stress is going, right? It's like, essentially the maximum stress is tangent to this curve or tangent to the circle. Okay. Now the other thing that can happen is that we decide to take the stresses right on this open face, like for this model. That can be a little bit dangerous. There's something called the Saint Venant principle, which says that you need to be a little bit away from where the loads are applied or the constraints are applied in order to be able to get kind of these ideal approximations. So in addition to not taking a node on this face,
I did take a node.
okay, yeah, so there can be some anomalies there. You want to take a node like over here or over here, a little bit down away, okay? And I think I talked about that also in the video. So if you go back, you can take a look. All right. But those are some of the things to consider. Do I expect it to be exactly the right answer? No. Okay. I mean, but it should be close. It should be,
It was like
within, I would say within, 5%, within 10%.
it was like 1,086, and I got like 940, which seems too.
Well, that's not so off.
That's not too off. That seemed too off to be like.
Well,
I thought it
so
is a-
that's off a little bit. So what can happen is you probably we were like go ahead.
Wasn't one of them supposed to be divided by 2? Because I thought I was like half.
Well, yeah. So it is. So that this is in the assignment we asked for the tensorial strain. Okay, and so the tensorial strain is half of the true shear strain. Okay, for shear, the tensorial shear strain is half of the true strain, and that the reason, or true shear strain, the reason that is because of the tensor map having to work. Okay, so pre-Pomax spits out tensorial strain, which is going to be half of the actual true shear strain. So I asked, and I got confused the last time we were here, but I asked in the last session, or when we went through it last time, in Canvas, I did put in that I was asking for epsilon 1, 2, or epsilon 1, 3, instead of this. Okay, but you're calculated right. So what you calculate on paper is going to be like gamma 1, 2 or gamma 1, 3. Okay, and what? So then you have to take half of that to figure out to give us the tensorial shear strain.
So Prepo Max was supposed to spit out something. I thought it was supposed to spit out something like double or half.
It is spitting out half, right?
Of what Canvas wanted.
No, it's supposed to be
Oh.
the same as what Canvas wanted.
Well, then mine was actually pretty. I mean, I'm still off by like 100, but
That's pretty
I-
close. You were within 10%.
I thought it was off by like.
No, so it sounds like you're pretty close.
All right, well that's. I didn't submit the screenshot.
Well, go ahead and submit it now.
Huh? It's on my computer. It's also
Oh.
too late. It will override my other answer.
Yeah, but the screenshot was worth more than.
Oh yeah. I guess I'll put it up when I'm
Yeah.
in front of my
Yeah,
computer.
yeah, yeah. Okay.
Do I have to change it, or can I just upload the screenshot for the answer to the question that I already submitted? 'Cause it's gonna change numbers. Should I make a new one?
Send us just upload the screenshot for what you already have, and then send us an email. Send Trevor an email.
Okay.
All right. Great. Thank you. Okay. Yeah. I can. Oh, because you have to change
Yeah. I don't really know.
Yeah, so there is okay. So there's a question here about so if you go to the office hours tab, okay, and you go down to this tab, this is very much related. Okay, very much related to question 3, right? It's under so it's under. Okay.
Yeah.
Okay.
Yes.
That nerdiness. Sorry.
You're really good. You're not. What I would do is yeah, you want to sketch on
It will be.
right, right, that's exactly right. So this value is the how far does it add?
I did it. I was with Augustin. I was just sitting down. I was literally on the right. I will use it. I'll use it for. It's like all land.
Or did all kind of oh one.
Oh.
Well, you're not going all the way up. Over two. That's right. Once you go across it,
I'm sorry.
But they're working on the report. Okay, so all right, what else? Yes. Well, it's and they're really close to each other, right? So Oh, it's right in front of us. Duh.
Now,
On the bottom, he did not create any margin.
Yeah, scan it up so the diameter is 1 centimeter.
yeah, but you need a pitch. So it's always possible. Yeah, the moment because you have to you probably want to pick a reference. You would do that. That's fine. That's fine. Yeah, that's fine. You just that doesn't make it very hard.
In the Y. No.
Because V is a constant.
So you take a look at the first
R is a constant. So I would suggest put like an O on that interface. Yeah. Yeah. And then now do this. That's right. You have to pick a spot. Well, there's also this. Right? Which you did account for properly before. So do the same thing again. So
reference point is defined as a salt section.
just write out what you know. So you know n is positive.
Where can we use crash?
It doesn't matter because that's the moment you apply to the structure. Z is always going to be no matter where because of well, it is, but even if it weren't, it's positive.
Region one of region.
But force is independent. The direction of the force is
I know it's false positive.
that's correct. Correct. That's fine. That's fine. Keep it away. Okay, then what? That's right.
Use that lower force of distance from.
Yeah. I don't know how you do on a.
I have my mouse.
Yeah, hit a mouse.
Positive or negative?
That gives me force of right.
Right, right. And then now where's it acting?
Is this selected?
Remember, if it has time to play. Yeah, you want to write it down. That's what I said. I think I tried to. Good. Good. Mr. Andrew. That's right. Yes, Samir. Hold on. Okay, so Byron. Yes. Oh, in the undeformed state, row, where it's okay, row. Okay. 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 Are you good? Or do you have? Are you good? Huh? Okay. Good. Good. Are you guys good? What's up? So, can you, if you, so this one, I see, what was the value of that again? 277. Okay, so something is, you got the right, ready row. What did you use for, the moment, for the applied moment, and what did you use for the shear modulus? What did you use for E and, what are your E and your, well, for both, right? So what are your, you had to put an E and a nu in the Primo Max, right? The new, okay, and then what did you put in for E? No, E should be 200, right? That's where it is. That's what's important. Right, because G is equal to E over quantity, or 2 times quantity 1 plus nu. No, no, you had to know that. Yes. No, well, no, that's what you had to pick, right? And because you see everybody in the, well, not everybody, but a lot of people in the group, and you're like, oh, yeah, shear modulus, right? It's like, yeah, you have to pick an E and a nu to get the shear modulus. And this is pretty characteristic for steel that you have a shear modulus. What it is around 79 gigapascals or something. Yeah. So put in like 200 gigapascals and like maybe put 0.3, and it should be pretty close. So that's what that's what. Yes, sir. That looks pretty good. Yeah. Oh, so So what is oh, I think I see it. Can you go right here? Can you click right here again? Yeah, the scale's not right. See, no, 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 that's right. Okay, no, no, I thought it was 100 meters. That was, is it you scaled by a factor of 1,000? Okay, that's probably the issue. Okay, so if you go, you can save this. You don't want to lose all this work, but let's just go back to the import set. Yeah, did you save this? Okay, so if you file new,
I'm deserving of a right answer.
I put 0 in and it never changed it to 0. So
Sure, right.
Try that.
Alright. Hold on. I'll go. No, we were definitely. What's up, Maya? How are you doing? So I haven't done it completely. To be honest, I think the transform could let you do it. But what I try to do in FreeCAD is I try to make sure that usually, with FreeCAD, if I keep it at the origin of FreeCAD, they're using SolidWorks. So, yeah, yeah. I'm not sure either. What was the length that you wanted to give your name? Okay, so one thing that's not right here is the scaling, right? You see, this is saying that this is like.
I said X was 0. My C value is wrong.
Oh, easy. You know, like this is 0.6 meters, right?
I think that is
So-
the issue.
You have to go. Yes.
So not a
What did you
calculator.
use? What did you do? Well, let's see. Maybe I'm wrong because that doesn't seem right. Correct?
Yeah, yeah.
I think I just got it. Wait, what you guys heard?
You can once you have a mesh, it's okay. You just have to work on the geometry tab. No, down low. Left down. See where it says geometry? And then it should let you. But that's weird. It now disappeared. Something's weird. Before you don't do anything, hit view and zoom to fit. Okay, that looks right. So I don't know why. Well, now that looks right. Yeah, I haven't had this problem. So if you go to art, go back, click on geometry, or no, sorry. If you go to geometry on now at the top. Art.
Wait, I don't have a belt. Or a
Oh,
belt.
there's not. Yeah, I don't know. It only lets you scale. I haven't messed with this. Yeah, using FreeCAD is like, it's honestly like 3 steps. But so I'm not quite sure what's going on here between SolidWorks and this, but FreeCAD it keeps one side of the origin. Okay. All right.
No. Yeah, actually.
Yeah.
I didn't get like the right answer. Like I got like 5 was your 2 for my answer, and then to go back to like 4 to 49 or something. So like it was close enough that I figured we could come up with my match. Oh no, I My Pro Max, like I can't even get over this. It's actually yeah, I think I'm gonna just yes.
But when it comes down to it, if I give you a geometry, the point is,
I'm trying to get down and.
so this is fine. I think this is great. It's very for the sake of being able to do the problem. Instead of looking at the answer. So you already found the reaction. That's right. Then you gotta do the cuts. And they're not, it's not super, it's not trivial. Okay? Not super trivial. What's up?
So we're on session.
What's going on? Well, which one is wrong? I mean, first, did you give it to, did Canvas tell you it was the right answer? What do you mean by your old equation? Yeah, that's right. Yes, that's good. That's how you do it. Okay. So what's your new G? What is your new G here? What the value that you picked? Just do a print. Just write it right here. Print G. Okay. That's a huge number. Do times 1 even minus 9. So it's it's a little off, not that off. Right. So maybe go to 210. But how far off are we? Are we still off by like a factor of 4? Yeah. So this is about right. So 210. All right. Okay. So what do you go into your EV model? No, that's supposed to be Young's modulus is less than 1. That's the issue. That should be 210 for the 200 for GPA. You can just type in GPA and it'll probably not that. What's your name? Matthew? Are you a 10? Okay. All right. Okay. Yes. Okay.
And I was going through the notes on here, and I was having a hard time. Like, I'm still really confused on like names and stuff, and trying to like say everything.
That's why.
Yeah,
I could tell. Like I was like, okay, who's training this stuff?
yeah, I was like really lost on it. So I was looking over here. So I
Yeah.
understand for this question we have to find the max volume.
I mean, that's the whole. That's the end goal. That's the end goal.
Right.
But it's not until this tab that we can actually do it.
Right, and I was looking at the functions that came up from here, and I was still like, wait, there's still like some missing pieces that I need to like, try to follow.
Okay.
Would you mind just trying to like explain this to? I'm sorry.
Yeah. So what happens is and if we graph it out, we can be able to see where it intersects. But how do you graph it out? Well, yeah. Yeah. So no, that's fine. So six. What did you do? 600. I'm using 7 differential, which is pretty close. So if you're using CME and E, looks like the math in the end. Here's E.
Yeah.
Okay. So what is so if you pull it out, what is the so really what I would say is this is the first thing is external fluid. Just break it down. First thing I have to do is external fluid. So first thing is figure out RL. What's the next thing after that? Yeah, so then you well actually for this method, write it out there. Not exactly. This method yellow it's
What red is calculating?
right? So then so that is equilibrium, but you have to figure out what your
Really,
so those are so we figure out the boundary.
So like I like started on
something around this yellow range, you can see if we getting 6
I'm
times 10 to the negative.
like, okay. And then I passed all the
Well, there has to be- there has to be-
Yes.
That's correct. So you can integrate.
So you're about there once you go out there.
Yeah, so what is W?
That's cursive. That's cursive. That's cursive. That's There we go. I don't follow the path. I always try. That's not necessary.
So A is equal to 0, right? Last if I get it to 0, but
And that's where the C's come from.
that's where the C comes in. So now, because now I've got a C1. So on the left side, we know that the B is equal to RL, right? That's internal shear force.
So that's C2.
So C1 is equal to RL. Okay. Still, right? Until you get.
Oh, this is the.
Do you have 8 and 9?
Thank you. Yeah, I just didn't know how to do so.
That's which is
That's true, right, because this equation, if there's no distributed, that's exactly, no distributed force. For the whole thing,
That I did.
and we know that, we also do the derivation that M hat does not so there, and if you look in the notes, right, pull up the notes, see if I'm right here, right? No, no, this is exactly, go up, go up on. Yeah, see, this is where, well, actually, go more, go up, go up. This is where delta V zero is at. So this is very, this is why. Okay, because equilibrium has to hold. Okay, we have G and taller massive. We have the outside and here, right? What's the point? Right? And so that's go up, right? It turns out that this is positive. What's confusing, right, is that n hat is in the opposite direction. N hat is actually negative. And still, n hat is both positive.
That's always good.
Okay, so it's important to write these down. Okay, so but we still think this is basically. Now we have economy to kind of get the over first.
Yeah,
So, yeah, so now we have
thought it
our
was
shear force.
What's the first three letters of the answer? Oh, the D.
Yeah, we integrated in, right? Yes. Yes, simple thing. Right? You have 0 to L over 4, L over 4 to 3L over 4, and then 3L over 4. So what happens is, right, is that this here is if we said the slope was RL, right? So that's all it is until we get to L over 4. So then it gets RL over 4, or RL L, L, right? Because it says slope start at the origin, that's the down position as well. That's H. Yeah, here. What happened when we got to L over 4? There was actually a drop, right, in the as it goes down, delta P. And it turns out, so my previous page is not happy because the shear force actually doesn't go negative. It still stays positive. But what we did is whatever that body is, like that lower guy. Okay, so now we have a new slope. It's still positive and it goes until 3L. And at 3L over 4, that's when we got to M hat. So where's the max? Yeah, exactly. It's gonna be 3 over 4. stable.
Oh. Can I get my test?
Alright, so.
No, that's exactly how I think. I got to the second page, and then, 'cause I didn't do the first page first. What was the first page? It was just like stuff from earlier that you just had.
Yeah.
Yeah, this should be posted on the
Okay. Oh, there's another question. Byron, okay, why is the flexure formula negative? Because when you plug sigma max back into the original sigma equation, then that should cancel out. Or am I looking at this? That was for part 2. Right. So they,
Yeah, Sean.
it is negative, right? We agree that it's okay. So I guess maybe I'll type in here. I don't know. Yes, I agree
I was just doing my name. My name is Sean Kemp.
that the original.
Well, that's the real.
I agree that the
I
original.
have 3 friends in this class that
What are we doing?
What's all three?
Okay, so my name's Sean Kemp. One's
Uh,
Dan Manson, Jason Lee, and Sean Shaw. But I mean, I wouldn't see me. Yeah, just Dan Manson.
let's not use other. Okay. Yes.
Okay.
Whoa. For the third question, why do you do this? Why is there distributed load on the right side?
Thank you.
Oh, this is for the overhang. Yeah. Sorry. Okay, sorry. I thought you went for the session 12. Okay. Yeah.
So,
Yeah. Yeah. That's right. Okay. Okay. Oh, okay. So be careful with this. All right. If you originally drew this careful. You can do this, but this is dangerous because then you change the direction of the executive team. So V is going to be, so if this were up, right, then the equal, right, if this were up, then this is down, then the equal, so F of V is going to be minus 1. No, but V does equal minus 1, right? The original way you drew it was that it's up.
My name's Riley Moss.
That's why it's okay. So then now.
What you mean?
Okay, so hold on a second. So where's the external? So you did the external. Let's do external first.
Exactly. Exactly. It's not in series.
So your external, right, is that's acting on the entirety of expanding one.
If it was here, then it would be in series. Damn, I messed up.
I mean, okay. So I don't see one right to the cut. Where's the external equilibrium? Oh, okay. F, A, and B. But there needs to be this force too. Oh, that's here. I see. Okay. And you're doing the moment of where? At the left side? At that point, okay. So that's a negative
No,
both
yeah,
negative, right? Well, if this is pointed upward, see, descending is. See, that's why I'm getting confused, because like if here and here, right? So if you drew it up, right, then it's a negative contribution. And this is also a negative contribution. So why? So that's weird, right? That should be a negative minus there. Okay. Okay, so that's fine. So then yeah, you're doing your cut. You have your effing. Yeah, you should be good. This should be fine. Okay.
This number's not speed.
Oh
no, it's not me.
I don't know.
My bad.
I don't remember. Yeah. But this part is pretty much, just so you know, it's pretty much all done on that exam.
I didn't see it.
You didn't see it?
Yeah.
It's
I
the
didn't
first-
want to see it.
Oh, yeah, okay, good.
This is my
But
bad.
all right, good. Yes, I can help you. Sure. Okay. So I'll just call the names. Max Kornvale, Nicholas Erickson, Rebecca Wisser, Kelly, Travis, Forrest, Chris Harrington,
Very good.
Brandon, Ibrahim Khan, William Weiss, Aaron Lipton, Byron E. Davis Castillo. You can just go over there, Trevor, and I'll go over here. Sudhi Suresh. Daniel, I think Daniel Chavez. Dennis Hine. Robert Elias. Tyler, Sam, Sydney Speakmer, Harkis,
Yes.
Colin Jaros, Vijay Havaru, Everett Murray, Michael
Hales.
Kirkland,
Yes.
William, Vidal, Silver, Mark Giordani, Nicholas, Med, okay, Mohammed, Nicholas, Med, Mohammed, Jude, Vile, Swaz, Swaz, yeah, Swaz, Sean Koski. Sarah Joe. Mohammed. Darren. Sid Shipping. Yesh Srivastava. Jolie Shum. Sidali Ragas Campos. Ben Stevens. Sarah. Thomas Kochi. Aaron Grossman.
Nice.
Yeher Mars. Kevin Hughes. Amir.
Were you actually guessing the whole time?
Yeah.
Damn. Oh, Pat.
Matthew Roman.
That one time. Impressive.
Sarne Mehta.
Yes, thank you.
Noah Lewis. Morgan Lazarus. John Moore. Zachary Solomon. Zachary Schwartz.
Oh yeah, I pulled that.
Is there anyone else we're missing? What's that?
I think in the beginning of the pile.
Yeah, yeah. I was gonna say,
AJ.
Yep, they're on the website. Okay, probably shut that off. Okay. Shutting down.